In this video, we're going to look at the use of quantum numbers to describe properties of electrons that reside within orbitals. And we will also discover that orbitals are grouped together in subshells and that subshells are grouped together in shells. So let's just take an opportunity to review what we know about electrons within electron clouds. We now know that electrons have both particle and wave-like properties, and that electrons are effectively distributed through space and not localized. We do not talk about electrons orbiting a nucleus in a well-defined trajectory where we can define both its exact energy and its exact location. Instead, we say that electrons reside in or occupy orbitals, which are regions of space that describe the likely location of electrons, assuming an electron actually occupies the orbital. We know that orbitals have a characteristic energy and that electrons can move between orbitals of different energy by absorbing or emitting energy, and typically by absorbing or emitting photons. Orbitals have a characteristic shape, and as you can see by these 7 orbital representations here, some of those shapes are often quite exotic. And we know that the orbitals have a characteristic orientation in space as well. For example, we can see the shape of an orbital might take on this dumbbell shape, but there can be 3 different orientations of that dumbbell shape, one along the x-axis, one along the y-axis, and one along the z-axis. The energy, shape, and orientation of orbitals are described and labelled by 3 quantum numbers, n, l, and ml. And they assist in describing the energy of the electrons and the distribution of electrons around a nucleus. And it is these quantum numbers that we're going to take a few minutes to talk about right now. Let's take a closer look at the principal quantum number n, which describes or defines the overall energy of an orbital and electrons in them. Well, it turns out that we've already met the principal quantum number n. This is a diagram of the energy levels in a hydrogen atom, and it shows absorption transitions and emission transitions that can occur for the single electron in a hydrogen atom. And these values here, n equals 1, n equals 2, 3, 4, etc., up to n equals infinity, actually refer to the principal quantum number n. So that if an electron resides in the n equals 1 energy level, or what we call the n equals 1 shell, it has a relatively low energy and exists relatively close to the nucleus compared to an electron that resides in the n equals 4 or 5 shell, where, relatively speaking, it has a higher energy and exists on average further from the nucleus. And so what we have here is the principal quantum number n defining the overall energy of an orbital and the overall energy of electrons that reside within that orbital. This diagram also shows that n takes on numerical values of positive integers, n equals 1, 2, 3, 4, up to n equals infinity. The higher the value of n, the higher the energy of electrons that occupy that particular orbital, and as n increases, the size of the orbitals increase. And as I said, electrons spend more time further from the nucleus, the higher the n value. It should also be noted that the size of the atom can be roughly defined as the size of the outermost orbital. Finally, let's get some useful language around this. Different orbitals, that is, different regions of space that have the same value of n, are said to belong to the same shell. So we talk about the n equals 1 shell, the n equals 2 shell, the n equals 3 shell, etc. The secondary quantum number L distinguishes orbitals within the same shell, or having the same n value, but having different shapes of electron distribution around the nucleus. And here you can see 4 of the many different shapes that orbitals can take, ranging from relatively simple spherical and dumbbell shapes on the left to really quite exotic shapes on the right. The shapes of orbitals are highly restricted and they are linked to the value of n, which means that the shell in which an orbital exists actually limits the shapes of orbitals that are allowed to exist in that shell. For example, spherical shaped orbitals, or s orbitals, can exist at every n level or in every shell, whereas this dumbbell shaped orbital, one of the 3 allowed p orbitals, can only exist in the n equals 2 shell or above. This double dumbbell shaped, one of 5 d orbitals that can exist, can only exist at the n equals 3 level or above. And this rather complex quadruple dumbbell shaped orbital on the right, one of 7 f orbitals that exist, can only exist at the n equals 4 level or above. One additional point that we need to make is that if the value of n limits the shapes of the orbitals that can exist in each shell, then the numerical value of n also limits the numerical value that L can take. For example, the allowed numerical values of L range from 0 up to any positive integer that is lower than n. In other words, 0 up to n minus 1. So the values of L will actually depend on the values of n. And that will become clearer a little later on when we see a visible or pictorial representation of orbitals, subshells, and shells. Orbitals and the electrons occupying them that have the same n value and the same L value are said to be in the same subshell. So the language we use here is that electrons reside in orbitals, orbitals are grouped together into subshells, and subshells are grouped together into shells. Historically, the second quantum number has been designated with letter designations, S, P, D, F, and G, instead of the numbers L equals 0, L equals 1, L equals 2, 3, 4, etc. And there is still a hangover from that labeling system. So what we see here in this table is that if an orbital has an L value of 0, we are talking about an S subshell, which has a spherically shaped distribution of electrons around the nucleus. If an orbital has an L value of 1, we are talking about a P subshell, which has a dumbbell-shaped distribution of electrons around the nucleus. If an orbital has an L value of 2, we are talking about a D subshell, which has the double dumbbell-shaped distribution of electrons around the nucleus. And finally, if an orbital has an L value of 3, we are talking about an F subshell, which can take on one of many exotic shapes of electron distribution around the nucleus, including this quadruple dumbbell-shaped distribution shown here. The subshells are named by noting both the energy level N and the letter designation. So you might see representations like a 3p subshell that represents a group of orbitals in the third n equals 3 shell, each having a dumbbell shape representative of p orbitals and characterized by having a principal quantum number of n equals 3 and a secondary quantum number of L equals 1. And we'll come across many more examples of subshell designations, such as, in order of increasing energy, 1s, 2s, 2p, 3s, 3p, 4s. In fact, technically, there are an infinite number of these subshell designations. And finally, subshell designations become very important for assigning and writing electron configurations a little later on, and therefore in determining a range of chemical properties of atoms, including how they bond with each other. The third quantum number used to characterize orbitals is the magnetic quantum number, ML, which distinguishes orbitals of a given n value and a given L value, meaning an orbital with a particular energy and shape, but where the orientation of the shape of the electron distribution is different. And just as the principal quantum number n limits the values for L, so the number of possible shapes L limits the number of possible orientations or values of ML, with the allowed values for ML being positive and negative integers, including 0, from -L up to +L. So what does that actually mean? Well, when the secondary quantum number L has a value of 0, the only value that ML can take is 0, which means there is only one possible orientation when L equals 0. And that sort of makes sense because when L equals 0, we are talking about s orbitals, and the distribution of electrons is spherical in shape, and there is only one orientation that a sphere can take around the x, y, and z axes. It also means, as we will see more clearly in just a moment, that there can only ever be one orbital in an s subshell. However, when L equals 1, and we're talking about p subshells when L equals 1, what we see is the value of ML can take values from -1 up to +1, including 0. So there are 3 possible orientations when L equals 0. And that means that there are 3 orbitals in a p subshell, each with a dumbbell shape, one oriented along the x-axis, one along the y-axis, and one along the z-axis. When L equals 2, we are talking about d subshells and orbitals within d subshells, with allowed ML values going from -2 up to +2, including 0, which means there are 5 possible orientations of electron distributions, which are represented here. It also means there are 5 orbitals in any d subshell. And then finally, when L equals 3, and we won't have to go any further than that, we are talking about an F subshell, and the allowed values for ML go from -3 up to +3, including 0, which leaves us with 7 possible orientations, meaning that 7 orbitals exist grouped together in an F subshell. And here are the quite complex shapes and orientations of the 7 orbitals within F subshells. Well, wow. That is a lot of abstract ideas to take in, and I wouldn't be surprised if you are a bit confused at this stage. Hopefully, however, we can remove some of that confusion by transferring what we have just seen to a scenario we have encountered before. And that is the electron energy level diagram for the hydrogen atom. We have seen previously that the single electron in a hydrogen atom can transition between any of these energy levels or shells by absorbing energy in the form of photons, or by emitting energy in the form of photons. What our new information tells us, however, is that within each of these energy levels or shells exists a bunch of subshells, each containing varying numbers of orbitals. So we can now redraw this energy level diagram for the hydrogen atom by showing all the orbitals that exist within subshells and all the subshells that exist within shells. And here we have a much more detailed energy level diagram for hydrogen, or what we call an orbital diagram, where all the possible orbitals that exist are represented by a horizontal line in this orbital diagram. And it's important to remember 2 things about these orbitals. 1, an orbital is simply a region of space where it is possible that an electron can exist. And 2, the properties of orbitals are characterized by the 3 quantum numbers which appear on this diagram, with the principal quantum number n given on the left-hand side, representing the overall energy of the orbitals within the n equals 1, 2, 3 shells, etc. You can see the secondary quantum number across the top, showing L equals 0, L equals 1, L equals 2, L equals 3, etc., corresponding to the different types of subshell designations of S, P, D, and F. The third quantum number, the magnetic quantum number, ML, is the number represented under each of the horizontal lines in this diagram. And for clarity purposes here, we are only showing them for the 4F subshell, where you can see they go from -3 all the way up to +3, including 0. If we focus again on the subshell designation, we see that for all the S subshells, there is only 1 orbital in each subshell, corresponding to only 1 possible orientation for the spherically shaped S orbitals. For the P subshells, we see that each subshell contains 3 orbitals corresponding to 3 possible dumbbell-shaped orientations. For the D subshells, we see that each subshell contains 5 orbitals corresponding to the 5 possible orientations. And finally, for the F subshells, we see that each subshell contains 7 orbitals corresponding to the 7 possible orientations of electron distribution. The last thing to point out on this diagram is that there is 1 orbital in the n equals 1 shell. And just note that 1 squared is 1. There are 4 orbitals in the n equals 2 shell, and note that 2 squared is 4. There are 9 or 3 squared orbitals in the n equals 3 shell, and there are 16 or 4 squared orbitals in the n equals 4 shell. There are also 4 subshells in the n equals 4 shell, 3 subshells in the n equals 3 shell, 2 subshells in the n equals 2 shell, and 1 subshell in the n equals 1 shell. It's also worth noting that the 1s subshell is an orbital, a subshell, and a shell all to itself. Finally, this table is a tabular representation of much of the same information, showing the allowed values of n and the allowed values of L at each n level, and the allowed values of ML for each L value. We can also see the subshell designations here corresponding to the n and L values for each subshell, and we can see the number of orbitals in each subshell for a given value of L, which incidentally is 2 times the value of L plus 1. And lastly, we can see the number of orbitals in each shell, which we just noted was equal to n squared. In the next video, we will investigate this orbital diagram for the single electron hydrogen atom in a bit more detail, and then follow that with a look at orbital diagrams for all the other multi-electron atoms.